Okay.
Just 1 second. I'm opening up the chat so I don't miss any questions if people post things in the chat. Okay, so shall I begin? Okay, so I am going to start with question 1A, and hopefully I will be able to guide you through the thought process necessary to actually answer this question properly. So like, I really hope that you guys will respond, give me feedback as much as possible so that, you know, we can try to make sure that we all understand how to answer this using like what we've learned in class so far. So question 1A is a protein involved in the recombination known as Rec-A binds to a single-stranded DNA and stretches the length of the strand. When the DNA is stretched by the protein, the bases are not evenly spaced. Instead, groups of nucleotides retain the B conformation while the phosphate backbone between them is extended, as shown schematically in the diagram below. While this kind of staggered distortion uses less energy than forcing a uniform separation between all of the base pairs. Describe the nature of the energetic resistance of the DNA to being uniformly stretched. So to answer this question, we really have to think about in what structure is DNA most stable. So can you guys give me like what the different conformations of DNA that we've talked about in class so far are? There are 3, but I'm looking just mainly for the 2. So there's B form as listed in the question. Awesome. And then of those three structures, which is the most stable form of DNA? What will you find DNA natively? Yes. Okay. And then what is the main driving force of like the actual formation of a B-stranded double helix? Yes. So if you were to pull the strand apart and it seems to be retaining its B conformation, and if you pull the strand apart, it reduces the amount of base stacking that is present. And like with those 2 pieces of information, you really can answer the question. Do you guys have any questions with regards to how to work through this question? Okay, I will move on then. Okay. So then for this next question, we're going to talk more about the actual sugar pucker. And can you guys tell me what the actual sugar puckers are for each of these diagrams below? So A, B, C, D. If you guys have any questions with regards to how the sugar pucker is determined, basically what you need to know is that the endo sugar pucker is on the same side as the C5 carbon, and the exo is on the opposite side of the C5 carbon. So then there are 4 different combinations of puckers that you've learned in the class, depending on which carbon that pucker is on. So can you guys tell me what this like A, the pucker for A is? Okay, yes, awesome. A is C2 endo, correct. B, C3 endo, yes. Okay, yes. So yes, A is C2 endo, B is C3 endo, C is C2 exo, and D is C3 endo. Perfect, awesome. Do you guys have any questions with regards to that? Feel free to unmute yourself or ask questions in the chat if you have any. Awesome. So then, which of these diagrams correspond to the allowed sugar puckers in DNA double helices? And please justify your answer. So which puckers do you think that DNA double helices would adopt? Okay, so in this question, you have to be careful to make sure that we're not talking about what the most favorable conformation is going to be, what the most favorable like pucker will be, but yeah, what the like what can be adopted. And it looks like Julian got it right, and they said that A and B can be adopted, and that would be correct. So if A is a B stranded double helix, what would B correspond with? Awesome. Cool. So C and D, they aren't adopted in like the 2 conformations that we learned about, like that DNA typically will adopt, which is the A and the B form. So yeah, the answer, like C and D will not be part of the answer. Awesome. And then, yeah, do you guys have any questions with regards to this one? If not, I will move on. Hopefully, okay, I need to hurry because I'm taking up too much time. Sorry. Okay, so which of the diagrams correspond with the allowed sugar puckers in DNA RNA double helices? And please justify your answer. Anybody? Okay, so C3 endo. Yes, so that would make sense. And then why would that be the case? So basically in this one, so you want to make sure that you're looking at the limitations of what is most like limited in the conformation it can adopt, and it is going to be this RNA strand here. So even if DNA can adopt that C2 endo, the RNA cannot, and it's gonna be limited by the conformation of the RNA group. And yes, that all looks correct. Everyone's participating. I feel so involved. It's very exciting. Okay, so then which of the diagrams correspond to the allowed sugar puckers in RNA double helices? Please justify your answer. Austin, are you asking about question part 3?
Number 3.
Okay, so in this, we're looking at like when we're trying to determine
Continue.
which sugar pucker it will adopt, we have to make sure, like we have to think about what kind of helix it's going to form. Is it going to form a A-form helix or a B-form helix? And in this question, like we said earlier, that DNA can adopt either the A-form or the B-form. However, RNA is limited in its capacity to form the A-form helix because of steric hindrance of the the 2' OH group. So because this is a complex between DNA and RNA, it's going to be limited sterically by the conformation that the RNA can adopt, which would be the A-form helix.
Okay, that makes sense. Thank you.
No problem. Okay, so then in this same question, we're going to have to look at what RNA double helices like can adopt and like what conformation, what form of nucleotide helix you would see. And it looks like you guys got that correct in the chat. Awesome. And then the last question would be, explain the most important consequences of the sugar pucker on nucleotides for transcriptional control and cellular regulation. So for this question, it's important to realize that the transcriptional control is going to be a protein-mediated interaction with DNA. And you have to think about how is that going to vary depending on the sugar pucker itself. Do you guys have any idea as to how that, what would make that the case? Awesome. So yeah, so it looks like you guys are all saying that it's about the ability to access the major groove, and that A-form helices are going to have a deeper, more narrow major groove, whereas the B-form helix will have more of a wider, more accessible groove to like the interacting proteins. And that is all that I have for you guys today. Thank you guys so much for participating. If you guys have any questions, feel free to ask me in the chat. You can private message me or just ask me in the general chat, and I will make sure I can answer to the best of my ability.
All right, so let's move on to question 2 then. I'll share my screen. All right, can everyone see my screen?
Yes.
All right, cool. So for question 2A, you're given the three forms of double helices, and you're asked to identify them and mark some of their properties. So I think for this, it would be helpful again to go over, just in summary, the properties of the major types of double helices. So can anyone give me the names of the three forms again?
A, B, Z.
Yep. All right, so there's three main properties that I want to look at for answering this question. The first of those is handedness. So can anyone tell me which of the three forms is the left-handed version of the helix? Right, yeah, everyone's got it. So the left-handed form is the Z form, and then all the other three forms adopt a right-handed helix. So the next property I want to look at is which macromolecules can adopt each of the helices. So can anyone tell me which molecules can adopt the A form?
RNA and DNA.
Yep, RNA and DNA. And for B form, can anyone tell me which molecules can adopt that? Right. And then Z form? Yep, DNA again. So yeah, again, this is just because of the different sugar puckers possible in ribose versus deoxyribose that only allows RNA to adopt the A form. So then the last property I want to consider is the major groove. So this is already talked about in the last problem, but can anyone remind me which of the three forms of DNA has the most accessible major groove? Right, yeah. The B form of DNA has the most accessible major groove. Just going to abbreviate that. But yeah, so now that we have this list of three properties, to identify each of these helices, we can sort of step through them in order. So first, let's look at handedness. Looking at this diagram, we can notice that the first of these forms is right-handed, the second of them is left-handed, and the third is right-handed. And if you're having trouble physically figuring out which one is left or right-handed, try curling your hands around the shape of the helix, and whichever hand of yours is actually able to do that, that's the handedness of the helix. So then from there, moving on to the next property, we can't tell this directly from this image, so let's just move on. Now looking at accessibility of the major groove, one thing I want you to notice is that of all of these over here, this appears to have a very large and open major groove, and while the others have comparatively less accessible minor grooves. So given that and the list of properties, you should be able to determine what forms each of these helices are now. And then moving on to the second part of the question. So again, all of this is just, again, stepping through this list of properties that we already know for each of the helices and filling it in accordingly. One thing I do want to point out in particular, though, is that for the third part of the question, it says that it results in negatively supercoiled DNA when the rest of the DNA is in B form. And the way I want you to think about that is that if the DNA is negatively supercoiled, then that means that, does that mean that the DNA is overwound or underwound? Right. Yeah. So it means that the rest of the B form DNA is underwound when this form of DNA is present. So does that mean that then it has the same or different handedness compared to the rest of the helix? Right. Yeah. So again, remember if like for example, let's say the B form DNA, we already know that's right-handed. If we're trying to underwind that, then whatever we're introducing must be turned the opposite direction. So this must be a left-handed DNA form, and that should help you fill in that. Right, yeah. So the supercoiling would depend on linking number, but in this case specifically, we're essentially given that assuming a normal piece of DNA, if the rest of it is in B form and this form is introduced, it will introduce negative supercoiling. So rather than talking about supercoiling of the entire DNA piece, we're talking about the effect of this specific change here. All right, and speaking of linking number, question 2b. So we're given a piece of DNA and a set of changes made to it, and we're supposed to assess the linking number of the closed circular DNA. So starting with part one, we see in part A, the DNA is just relaxed and open and 1,000 base pairs, and it's just closed. And we're asked to find the linking number of the closed DNA. So we're already given that the rotation per base pair is 36 degrees. So again, to find the number of base pairs per turn, we know that one turn is 360 degrees. And if we just divide that by the rotation per base pair, we get that the number of base pairs per turn is 10. So from here, we know that there are 1,000 base pairs total, and there's 10 base pairs per turn. So can anyone remind me what the equation is for finding the linking number? Right, yeah. So the linking number is equal to the twist plus writhe. We can find the twist from this. Does anyone know, can anyone tell me what the writhe is in this setup? Right, yeah. So in this setup, the DNA is completely relaxed, so we don't have any writhe introduced. And we can find the twist just by knowing that we have 1,000 base pairs long DNA, and there are 10 turns per base pair, and that should give you an answer, which for the rest of the problem, we're just going to call A. Oh, sorry. There we go. So then in part 2 of the question, in the process marked B, the same piece of DNA starts in the same way, and then we introduce 4 turns of zDNA, which are each flanked by unwound DNA, and then we close the loop together. So for this problem, the way I want you to think about this is that given that we have, let's say, a twist of A for a perfectly relaxed piece of DNA in setup from part A, now we want to know what each of these changes would do to the closed piece of DNA. So the first thing I want you to think about is that for these 4 turns of DNA, for the 4 turns of zDNA that were converted from the original B-form DNA, for each of those turns of zDNA, by how much do we change the linking number and in which direction do we change it? Right, yeah, so a few of you have got this. But yeah, you need to be careful when looking at this problem. Initially, you might just think that since BDNA is right-handed and ZDNA is left-handed helix, then each one would might decrease by -1. But you do have to watch out for that, because in order to convert a right-handed helix to a left-handed helix, you would first have to unwind it. So that's -1. And then you would have to turn it left-handed. So that's another -1. So the total change is -2. So then from this original A amount, we would subtract 4 turns times 2 changes per turn. And then finally, we're also given that each ddNA segment is flanked by 1 turn of unwound DNA. So we have 2 turns, 1 on each side, where the DNA is unwound once. So that's just going to reduce by 2 again. And this should give you your final answer. Yeah, I guess in this case, we're not taking into account the different number of base pairs per turn because we're given that 4 turns of zDNA are introduced. So we're given the amount of turns directly. We don't have to contend with base pair number. Okay, yeah. So for why we subtract 2, remember, we start with bDNA, which is a right-handed helix. Sorry, let me explain why we subtract 2 first. But yeah, we start with bDNA, which is a right-handed helix, right? And then if we want to convert one of these turns to zDNA, we know that zDNA has to be a left-handed helix. So our final result will look something like this. So for each one of these turns that we convert, we first have to completely unwind the turn to completely straighten it. And that changes the twist by -1. And then we turn it once more to the left, changing the twist by -1 again. So the total change is -2. And which formula did you say you were confused by? Oh, sorry, yeah. So this is the number of turns of zDNA. And the 2 is the change per turn. So yeah, essentially, we're introducing 4 turns of zDNA, and for each of those turns, we have to subtract 2 from the original twist. So that's where this 4 times 2 came from. Sorry if that was written unclearly.
So for the rise that would occur, does that just correlate directly to the 4 turns of zDNA, or does that also you have to subtract it by 10 or it's -10? You know?
Right, yeah. So for the ride that would occur, that is basically just from this. But the reason I'm writing it out this way is first because it might be easier to think about going step by step from the initial result once you already have the result from the previous part. And then also since we're turning this before combining it, it might be easier to think of it as the original twist of the thing before closing it together. But yeah, if you work it out through the write, it should give you just this exact same number. And the subtraction of 2 at the end is because the zDNA segment is flanked by 1 turn of unwound DNA on each side. So on each side of this, there's 1 turn of DNA that's been completely unwound. So we subtract 1 for each of those. All right, so that's all for question 2. I'm going to stop screen sharing and feel free to ask more questions in chat if you have them.
All right, I'll be running question 3. All right, so yeah, if you have any questions, feel free to ask during the presentation. All right, so for 3A, it's asking to fill in the skeleton of 2 deoxyribose rings for a single strand of DNA and to label the 3' and 5' ends and show the phosphate groups. So a good way to start doing this would be to number the carbons of the ribose ring. So 1 second, yeah. So here you can see they're numbered 1 through 5. And you can sort of identify some critical features based on the number of carbon in the ring. And don't forget to also include the oxygen in the ribose ring. So the 1' carbon will have a base bounded to it. And the 2' carbon will have a hydroxyl, or won't have a hydroxyl, because this is deoxyribose DNA. So you can begin to fill in the phosphates here, and you'll see bases attached to the 1' and the 2' hydrogen, and the phosphodiester linkage. And so that brings to like 3 sort of important points about this structure. The lack of a hydroxyl group on DNA allows it to have that 2' endo sugar pucker that allows bDNA formation. And 2 important points that'll come up later in the question is the negatively charged phosphate backbone, which is seen through each linkage, and the fact that this DNA is synthesized in the 5' to 3' direction, which we'll see more later. So yeah, here's the basic structure of the DNA. Does anyone have any questions so far? I don't know if I can see chat. Oh, there we go. All right. So the next question asks, suppose an organism uses nucleotides such as the molecule 2' deoxyadenosine 3' triphosphate for its DNA synthesis, and how would the mechanism of polymerization of DNA differ? So seen here is just some generic normal nucleotides. And so in the normal case, the 3' hydroxyl group would attack the innermost phosphate, and that would kick out a pyrophosphate. And that would ultimately be 5' to 3' synthesis, because once that they polymerize, the 5' end would be sticking out at the top, and the new nucleotide would have a 3' end. So for this question, if you look at the name of the molecule, you'll notice that it's a 3' triphosphate, which means you can imagine that this 5' triphosphate is now on the 3' end, but the hydroxyl is still going to be the one that's going to act as a nucleophile. So even though the triphosphate's now at the 3' end, to attack the triphosphate. So it's basically DNA polymerization is going to be in the opposite direction as 5' to 3' to fit how this molecule works. Yeah, so it attacks itself. So I mean, sorry, I'm trying to, oops. Okay, there we go. Yeah, so if these are like two separate, okay, I see what you mean. So it wouldn't attack itself, but the hydroxyl would now, there would, instead of a triphosphate on the 5' end, there would be a hydroxyl, and that would attack a different nucleotide, which would now have its triphosphate on the 3' end. So yeah, it wouldn't attack itself. Yeah, so there would be an OH group on carbon 5 now because it's a 3' triphosphate. So if you just imagine this 5' triphosphate detaches, and it's now where the 3' hydroxyl is. Does that make sense? Yeah. Sorry if that was unclear, but yeah, this is still the normal nucleotides, but I guess you'd have to imagine that the 5' triphosphate and 3' hydroxyl group like switched in this case to match the question. Yeah, sorry. Yeah, so the OH group is nucleophilic. It's more electronegative. So I guess it's sort of semantics, but I guess it'll like attack the triphosphate. But I mean, basically, yeah, it's going to be the one forming the bond with the triphosphate. Yeah.
So what's the 2' in reference to in the question?
So that I think the 2' referring to the deoxy, right? That, yeah, there's no hydroxyl group at the 2' end, or at the 2' carbon, which is characteristic of DNA. Yeah. All right. Yeah. So the OH. So regardless of whether the OH is at the 3' or 5' end for this question, it'll attack the alpha phosphate, which I think is the innermost phosphate. All right. Yeah, so yeah, it would be the opposite. The same mechanism, but the opposite direction. So if you have more questions about that, just put it in chat. But for the next question, it's saying chemists have made derivatives of DNA and RNA with an amide bond, like a peptide, instead of phosphodiester linkage. And surprisingly, they form double helices, and these double helices are significantly more stable than DNA and RNA. So you can go back to some of the other questions for this homework, and the important one major concept is that the major contributor to DNA helix formation is base stacking between sort of bases stacking and twisting on the same strand. So if you replaced the backbone of DNA with a different backbone, as long as the linkage is generally the same and can still properly link the stack, the helix, it wouldn't be too unreasonable that a helix would be helix formation would be promoted due to base stacking interactions. So that factors into part of the question, but the other part is why it's more stable than regular DNA and RNA. So if you think back to the part one of this question with the basic skeleton, yeah, that's getting in the right direction. But yeah, if you think back to the basic skeleton, you'll remember that negatively charged phosphate backbone. And that is, since there's a bunch of phosphodiester linkages with negative charges, that's going to contribute to repulsion. So you can now compare that to the this peptide bond, which this is a generic amino acid, but you can see the peptide bond in the middle here. So you can imagine like that would be the type of linkage forming in this new DNA derivative. So yeah, as someone said in chat, yeah, so I think metal ion coordination does attenuate the repulsion, but I believe if you have a neutral charge, it would even further increase the stability. Though, yeah, maybe it would, yeah, is that more beneficial than if it's not negative because less repulsion? Yes, well, so yeah, the peptide bond will be neutral, so you'll get rid of that original phosphodiester repulsion. And ultimately, that'll likely make the DNA more stable. Does that make sense? All right. So the next question shows two different DNA molecules with a different segment of sequence, and you're given that the scientist finds they measure the melting points for each DNA sequence, and they find different results. For DNA 1 and DNA 2, they would melt at different temperatures. So the question isn't asking why or like why one sequence melts at lower temperature than the other, but it's asking why that difference exists in the first place. So you can start by thinking of the molecular interactions between each strand. And so if you first look at the base pairing interactions seen between each strand, which is in the circle, if you start to compare them, you'll see, regardless, in each case, it's adenine, thymine, and the same for DNA 2. So this would probably be unlikely to contribute to any sort of difference. But going back to the earlier concepts, you know that the major contributor to strand formation is the base stacking. So if you look at the strands from another perspective, the base stacking interactions on the same strand, you'll see that they're actually different for DNA 1 and DNA 2. Because strand 1, you'll see adenine, thymine, and strand 1 of DNA 2, you'll see all adenines. And ultimately, if you imagine base stacking as like the electrostatic interactions between each base on the same strand, they're going to have different charge distributions, which could lead to different strengths, which ultimately would probably contribute to the melting point's difference. Does that make sense to everyone? All right, that's all I have. Yeah, no, you don't have to explain why it's stronger. Yeah, you just have to explain why there is a difference in the first place. Like what is causing the difference? Yeah.
Okay, so I will go over question 4. And so first I am going to quickly, like really quickly for the sake of time, review the basic premise behind supercoiling. So supercoiling is basically a way that DNA compensates for any tension that's introduced into it. So in B-form DNA, base pairs of B-form DNA are stacked on top of each other at a 36-degree angle, and this is the most optimal or lowest energy angle between the base pairs because it allows for favorable electrostatic interactions. So however, if I imagine rotating the two strands of DNA to divert the base pairs from each other and from their optimal angle, the stacked bases would no longer be able to form these favorable electrostatic interactions, and this would introduce tension into the helix. And this tension must be resolved in one of two ways. So if one end of the DNA is free, then rotating the DNA one way will simply result in the helix rotating back to its original position. However, if we rotate one end and then fix the two ends of DNA in place, then the helix is not able to rotate back to its original position. And this is where supercoiling comes in to resolve tension. So there are three important parameters, as we've learned, to describe the process of supercoiling: linking number, twist, and writhe. Linking number is the number of times that one DNA strand passes around another. And there are two important things to remember. First, that linking number doesn't change if both ends of the helix are fixed. So we'll see this in question 4. And the second thing is that in relaxed DNA, meaning not supercoiled and with no tension that's introduced into it, the linking number is equal to the number of turns. This can be calculated using the base pairs per turn ratio, which were given in the question. Then twist is the number of turns that both strands make around the helix axis. And this means that in relaxed DNA, since the twist is equal to the number of turns, the twist is also equal to the linking number. Then finally, writhe is the number of times that one double helix passes over another. And we say that DNA is positively supercoiled if it has a positive writhe, negatively supercoiled if it has a negative writhe, and there's no supercoiling if the writhe is 0. And then finally, this important equation that we know to be always true is that linking number is equal to twist plus writhe. Okay, so question 4a, we're given completely relaxed DNA where one end is fixed and the other end is free to rotate initially. So first, we can determine the linking number for this situation. So we know that the DNA contains 3,300 base pairs, and we also are given the base pairs per turn ratio. So the way that we can calculate linking number initially is just by multiplying by the base pairs per turn ratio. So there are 11 base pairs per turn. That would mean that there are 300 turns total. Just zoom in. 300 turns total, and that would mean that the linking number is 300. And then what about the twist? The twist is equal to the number of turns. So since this is relaxed DNA, twist is equal to linking number, which is 300. And then how about writhe in this initial relaxed DNA? Since there is no supercoiling that has happened, and since linking number and twist are equal to each other, the writhe will be 0. Next, we're given that the DNA is rotated by 3 full turns in a left-handed sense. So when we're considering left-handed and right-handed turns, we can think of it as introducing more or less turns in the DNA. So since the formed DNA is right-handed, that would mean that if we introduce left-handed turns into it, this would decrease the number of turns in DNA. So this is going to decrease both the linking number and twist by 3. So linking number will be 297. This is after the rotations have occurred, but before the DNA is fixed or supercoiled. This is just an intermediate part of the process. And since linking number and twist are both equal, writhe is equal to 0. And finally, the ends are fixed. So once the ends are fixed, the linking number can't change. So it will stay at this new value of 297. The twist, however, is the most stable at its original relaxed value of 300. So the twist will go back to 300. And so in order for the twist to go back to 300, the writhe needs to compensate. And to determine by how much the rise compensates, we can use our trusty equation. And we know the 297, the linking number is equal to 300, the twist plus writhe. And we can use this to solve for the writhe after the rotations. And then in part two asks, will the DNA be relaxed, negatively supercoiled, or positively supercoiled at the end? Well, we can just determine this from the final sign of the writhe, because the sign of the writhe can tell us whether the DNA is positively or negatively supercoiled. We know that it won't be relaxed because now it has tension that's introduced into it. And so in order to make up for that tension, it's going to have to be either positively or negatively supercoiled. But the sign of supercoiling, we can just determine from the sign of the writhe. All right. Let me see if there are any questions. No, okay. All right, so for part B, we can consider that there is DNA polymerase that is replicating DNA while both ends of the DNA are fixed. So note that here, the initial conditions in this case is that both ends of the DNA are already fixed as compared to part A, in which the DNA is initially free to rotate. So this condition is going to affect the twist and the linking number throughout the process. So because this means the linking number can't change, but twist, or the number of turns, can change. So part one asks how the twist changes when the polymerase adds new nucleotides and after supercoiling. So can someone either shout out or say in the chat what would happen to the twist? Right, so yeah, you guys are saying increase, and that is correct because the polymerase is adding new nucleotides, and as we're adding new nucleotides, it also adds new turns. So this increases the number of turns, and thus it increases the twist. So addition of nucleotides always increases the number of turns. Part two asks, will the linking number increase, decrease, or stay the same? And in this case, we know that since both ends are fixed, we know that the linking number can't change in this case. So the linking number will stay the same. And then part three asks how the writhe changes. This is after supercoiling has occurred. So in order to determine the writhe, we can again use the same equation. And we know that from part one that the twist is going to increase. And we know from part two that the linking number is going to stay the same. So in order for the linking number to stay the same, the writhe will have to decrease by the same amount that the twist is increasing. So the writhe will decrease in order to compensate for the increase in twist. And then finally, in part four, we are given these three different conformations of DNA, and based on the type of supercoiling that's happening here, we can determine what the DNA will look like. So in part A, there is no supercoiling that's happening, but part B and C are different types of solenoids. So can someone tell me, first of all, whether positive or negative supercoiling will occur here? So that's correct. Since writhe is decreasing as the polymerase progresses, the supercoiling will become more and more negative. So that's true. So would that indicate a right-handed or left-handed solenoid? That's right. So since we have negative supercoiling, this would result in a left-handed solenoid. And then from that, we can just see which of these corresponds to a left-handed solenoid. So that is all. Are there any questions? Should probably move on to the next question. Right. Okay, you can just go ahead.
Hello, I will be talking about question 5. You should be able to see my clipboard now. All right. So question 5 is really just testing you on testing whether you know the defining characteristics of a lot of these different bases, a lot of these different amino acid residues. So for the first part of question 5, you are given this top-down view of the from the major groove of a base pair. Now I can redraw this as, so since you know the top is the major groove, you can write the major groove here, where this will be your H1 acceptor, this will be your H1 donor, and then on the other side you will have your H1 acceptor and your methyl group. This should look similar to a diagram you've seen in lecture, and you should be able to tell from this what these two base pairs are. Alternatively, you can also just look at this group, which is a methyl group, and you should be able to tell from there. You can also tell from there that there's only one real base with a methyl group there, and you can tell from the other base from the canonical base pair. Moving on to 2, you have 2 alpha carbons here for the residues, and for these residues to specifically interact with this base pair, they must have a complementary interaction. So for this H1 acceptor, you will need an H1 donor from the alpha carbon, and for this H1 donor, you'll need an H1 acceptor. For the second part, you'll have the alpha carbon here, and you'll need something that to interact with this H1 acceptor, which will be an H1 donor. And you'll need something to interact with this methyl group, which has to be another hydrophobic group. Now, looking at an amino acid chart or just from your memory, you should be able to tell, you should be able to match these characteristics, H1 donor, H1 acceptor, to at least two amino acids that should share this kind of configuration, and there should be only one that has this configuration with an H1 donor and a methyl group. For this last part, part 3, you're told that you're asked whether an alpha helix can make an interaction with the major groove edge in an RNA double helix. And to answer this question, you should remember the key differences between what DNA and RNA normally look like. So for DNA, you have that C2 prime endo pucker, the sugar pucker, and for this one, you have a C3 prime endo sugar pucker. And from questions 1 and 2, you should remember that whether what these sugar puckers change for the major group width. And you should know whether the major groove is larger or smaller for RNA. And from that, you should be able to answer the question, since an alpha helix can access the major groove of the DNA because it is relatively large compared to the minor groove. For the second part of part 3, they ask why this base pair that you identified in part 1 is not naturally present in RNA. And to answer that question, you should remember what the normal base pairs are for DNA. You have AT and GC. So now you should answer what base pairs are there for RNA and what is missing. And from that, you should be able to answer why the base pair you have in part 1 is not naturally present in RNA. And that should be question 5. Are there any questions? part 1 will ask you for the base pair, and part 2 will ask you for the amino acid residues.
I was just wondering, where will the recording be posted?
We'll post it on Piazza, likely in the same folder as the concept lecture slides.
Okay, thank you.